Multivariate distributions. In order to know about the distribution of two random variables, it's not enough to know the probability of the various values of x and the probability of the various values of y. We need to know the joint probabilities, the probabilities of pairs of values, because this includes information about the possible dependence between x and y. The joint probability function, usually denoted f of x comma y, is the probability of a specific pair of values, x, y, or the probability that the random variable x takes a specific value, little x, and y takes the value, little y. In such expressions, we often replace the word and by a comma. And this function, f of little x comma y, is called the joint probability function of the two random variables. If we have more than two, say little n random variables, capital X1 up to capital Xn, then the joint probability function is a function of n arguments, which again describes the probability of all possible combinations of values for those n random variables x1 up to xn. So f of x1, x sub 2 up to x sub n represents the probability that capital X1 takes the first value, little x1, and capital X2, the value little x2, up to capital Xn takes the value little xn. Properties of a joint probability function. Let's return to the so-called bivariate case, the case where little n equals 2. We're looking at two random variables, x and y. The first property is non-negativity. Probabilities are non-negative, and so therefore are joint probability functions. Little f of x, y is greater than or equal to 0 for all values of little x, little y. Moreover, the sum of the probability of every possible combination of x and y must be 1. The sum over all possible pair of values, little x, little y, f of x comma y, is therefore equal to 1. If the sum of non-negative values f of xy over all xy is equal to 1, this means, of course, each one of them is less than or equal to 1. That's obvious in any case, since those represent probabilities. Every value of f of xy is between 0 and 1. So that's a consequence of the first two properties. Joint probability functions. Rather than to provide a formula for the function f of xy, it's common to give a joint probability function in terms of a table of values, as below. So, for example, when x equals 0 and y equals 0, f of 0 comma 0 is equal to 1/8, according to this table. Here, x can take the values 0, 1, 3, and 4, and y takes the values 0 or 1. The pair of values, x equals 0 and y equals 1, has probability 0, for example. And if you add up all the entries in the table, you're summing over all possible pairs, you obtain a total of 1. We're asked here to determine the probability y equals 0, the probability y equals 1, and the probability that x is strictly bigger than y. To get the marginal probability that y is equal to 0, we add up the values in the first row of this table, the row corresponding to y equals 0. 1/8 plus 2/8 plus 1/8 is 1/2. To get the probability y equals 1, we add up the corresponding row for y equals 1, and again we get a sum of 1/2. Those two values constitute the distribution of y, usually referred to as the marginal distribution for the random variable y. Finally, what's the probability that x is strictly larger than y? We have to identify the entries in the table for which that's the case, and those entries correspond to y equals 0 and x equals 1 or 3, or y is equal to 1 and x is equal to 3 or 4. Adding the probability of those four pairs of values together, 2/8 plus 1/8 plus 2/8 plus 1/8, we obtain 6/8. Marginal probability functions. In the last example, we obtained the distribution of y by adding up the probabilities corresponding to a given value of y is equal to 0, all the probabilities in the first row of the matrix for the joint probability function. And when we took the sum of the values in the second row, that gave us the probability that y was equal to 1. A distribution of one of the random variables obtained by adding all the values in one row or column is referred to as the marginal probability function for a random variable x or y. For example, the marginal probability function for x, often denoted with f sub x of x or f sub 1 of x, is obtained by fixing the value of x and adding over all values of y the probability f of x comma y. Similarly, the marginal probability function for y, denoted with f sub y of y, or f2 of y, is obtained by holding that value of y constant while adding over all possible values for x. These are simply the distributions of the random variables x or y. The word marginal is attached only to remind you that it was obtained from a joint probability function. Example: minimum and maximum on 2 dice. I throw 2 dice, and I define 2 random variables as a result. X is the maximum of the 2 numbers I observe, and y is the minimum of the 2 numbers. We're to find the joint probability function of x and y, the marginal probability functions of x and also of y, and the expected value of y, the minimum. So let's start by determining the joint probability function. And we'll begin with a value of x strictly bigger than y, where both x and y are in the interval between 1 and 6. The joint probability function, f of xy, is the probability x takes the value little x, y takes the value little y. And because x and y are different, this can occur in 2 possible ways. The first die, or the red die, say, is equal to x, while the green die is y, or the red die could be y, and the green die could be x. 2 out of 36 possible ways, so that's the probability that x equals x, y is equal to y. What if y is bigger than x? Remember that y represents the value of the minimum, x the value of the maximum. It's impossible for the minimum to be larger than the maximum, so in this case the joint probability function f of xy is equal to 0. Now suppose little x and little y are the same, little x equals little y. In this case there's only one pair of values yielding that common value of x and y, 1 out of 36 possibilities. So in summary, we've established the joint probability function f of xy is 2 over 36 when x is bigger than y, 1 over 36 when x is equal to y, and 0 when x is less than y. And as a cross-check, you should add over all values of x and y to make sure that those numbers add up to a total of 1. What's the marginal probability function of x? What's the probability that the random variable x takes a given value little x, or f1 of x, or f sub x of x? We obtain this by holding that value of x constant and adding the joint probability function over all possible values of y. How many possible values of y are there? Suppose x is equal to 3, for example. Then y can be 1, 2, or 3, but not greater. The values of y that are less than x, strictly less than x, have probability 2 over 36. The value of y equal to x has probability 1 over 36. So the sum is 2 over 36 times x minus 1 plus 1 over 36, or 2x minus 1 divided by 36. That's the marginal distribution for x. X ranges from the values 1 up to 6. Similarly, we can calculate the marginal probability function for y. In this case, we hold y constant at a fixed value and add over all the possible values of x, which are y or greater. There is one value of x that's equal to y, that has probability 1 over 36, and there are 6 minus y values that are strictly bigger than y, each of which has probability 2 over 36. When we add those together, we get 13 minus 2y over 36, so that gives us the marginal distribution of y, given below in a formula and in a table of values. Note that if we're required to determine the expected value of y, we can do that in the usual fashion from this probability function by adding together the possible values of y times the probability of those values, f2 of y, which in this case turns out to be the sum of y times 13 minus 2y over 36, or around 2.5278. So the expected value of the minimum is around 2.5. What's the expected value of the maximum of the number, x, you obtain on a throw of 2 dice? Well, the average die has expected value 3.5. The minimum, as you might expect, has smaller expected value. The maximum, larger. The expected value of x is close to 4.5. Review problem 1. The joint probability function f of x, y of a pair of dependent random variables is given in the table below. From the two random variables x and y, I'm going to define a third random variable called r. R is x minus y, the difference between x and y. What's the distribution of the random variable r? Solution. What I've had to do in order to determine the solution for this problem is establish the value of r corresponding to each of the pair of values in the table, the pair of values for x and y. So for example, in the first cell, x is equal to 0 and y is equal to 0. R, which is x minus y, is also 0, 0 minus 0. In the second entry in the first row, x is 1, y is 0. X minus 1 is equal to 1. So in this table, I've written the values of r corresponding to each pair for x and y, and you'll notice that r equals 0 occurs twice in the table. R equals 1 also twice. So below this, we've compiled the possible unique values for r and their corresponding probability. For example, r can run anywhere from -1 up to 3, but the probability of the two extreme values, -1 and 3, are both 0. The probability r equals 0, for example, is obtained by adding together the probability of the two cases in the above table, which lead to that, namely x and y equal to 0, and x and y both equal to 1. That's 1/8 plus 1/8, or 2/8. Similarly, the probability r equals 1 is the sum of two cases, two values, both of which are 2/8, to give 4/8. And finally, the probability r equals 2, again 1/8 plus 1/8, or 2/8. Independent random variables. Two random variables, x and y, are said to be independent if knowledge of the value on one of them, say x equals little x, in no way affects the probabilities you would assign to y. In other words, the events, capital X equals little x, and the event y equals little y, are independent events for all pairs of values little x, little y. Another way of saying this is that the probability that capital X equals little x and y equals little y is the product of the probabilities, the probability x equals little x times the probability y equals little y. That's what we mean in general by independent events. The probability of an intersection is the product of the probabilities. Written in terms of joint and marginal probability functions, this says that the joint probability function f of xy factors into two parts. The marginal probability function for x, f1 of x, times the marginal probability function for y, f2 of y. And of course, for a function to factor, what that means is that holds for all values, all possible pairs of values, x, y. When two random variables are not independent, we refer to them as dependent. It can be highly dependent or just a little bit dependent. In this course, we won't be able to specify to what degree they're dependent, except in special cases. Here's an example. Below, we've written the joint probability function, f of xy, in the form of a table. We've also written the marginal probability functions for y and x, and in this case, we've added up values so that the marginal probability function appears in the margin of the table. For example, in the bottom row, you see the marginal distribution for x. And in the right-hand column, you see the marginal distribution for y. This table is special. Take the entry in the upper left-hand corner, for example, 0.1. This is obtained by multiplying together probability that x equals 0, bottom left, 0.2, times 0.5, which appears in the upper right-hand corner of the table, the corresponding probability that y equals 0. F of 0, 0 is f1 of 0 times f2 of 0. If I were to erase the entries in the table itself and leave only the margins, you could reproduce all the numbers in the table. This is indicative of independent random variables x and y. Here's another more obvious example, in fact, of independent random variables. I throw a die twice. X is the value I obtained on the first throw, and y the value I obtained on the second throw. The question is, are x and y independent of one another? Intuitively, the answer is obvious. The first throw can't affect the value we obtained on the second. To prove this mathematically, we write down the marginal probability function for x, probability x equals little x, 1/6 for all values of x from 1 up to 6. And the marginal probability function for y, the probability y equals little y, is also 1/6 as y goes from 1 up to 6. What if we take a pair of values, little x, little y? What's the joint probability function? It's the probability of that pair, 1/6 times 1/6, or 1 over 36. And since this is identical to the probability that x equals little x, and times the probability that y equals little y, x and y are independent random variables. The joint probability function factors into the product of the two marginals for all values of little x and y. They're independent random variables. Independent random variables when there are more than two. Let's suppose I have random variables capital X1, capital X2 up to capital Xn. We say they're independent if for every possible choice of values, little x1, little x2 up to little xn, then the events capital X1 equals little x1, capital X2 equals little x2, and so on, those are all independent events. This means that their joint probability function will factor into the product of the individual marginal probability functions, f1 of x1 times f2 of x2 times fn of xn. And indeed, this in turn means that if you were to give me the marginal probability functions, I could determine the joint probability function, little f. Review problem 2. This problem concerns independence. Suppose I have two random variables x and y with the joint probability function specified in the table below. The question is, are the two random variables, x and y, independent of each other? You're offered several possible answers. One is true, the second is false, the third is no, they're mutually exclusive, and D, it depends on whether x lives in y's basement or not. Solution. Let me begin by ruling out some answers. Random variables don't typically have basements, so D is out. Random variables are not sets or events. They can't be mutually exclusive, whereas events can. C is out. So we're left with independent or dependent. In order to determine that, we need to check whether the joint probability function factors into the product of the two marginal probabilities. Let's look at one entry in the table, for example, the probability x equals 0 and y equals 0, which is 1/12 according to the table. We'll compare that with the probability of x equals 0 times the probability y equals 0. And if I compute the probability x equals 0, it's the sum of three values. It turns out to be 3/12. If I compute the probability y equals 0, again, it's the sum of three values. It turns out to be 1/3. And so in this case, we do have a factorization. The probability x equals 0 and y equals 0 is the product p of x equals 0 times p of y equals 0. But this does not prove that x and y are independent. We need to have a factorization like that for every pair of values. Let's take another, x equals 1 and y equals 1. That joint probability is 1/3, whereas when I computed the probability x equals 1, I got 5/12, and the probability y equals 1, I got 2/3. The joint probability in this case is not equal to the product of the two marginal probabilities. So the random variables x and y are not independent, they're dependent.